When we try to understand the true scale of the Milky Way, our journey doesn't begin in the galactic center or at the edge of the spiral arms. It begins here, right where our own solar system drifts through a quiet-looking region called the Orion Arm. From our point of view, space appears calm, almost serene. The stars seem fixed in the night sky. The Milky Way stretches above us like a silent river of light. But this calm is an illusion, because even this gentle stretch of space is part of something far larger, far more dynamic, and far more powerful than anything we can directly perceive. Everything here moves. Everything is pulled, accelerated, pushed, stretched, twisted. Every star, every cloud of gas, every drifting grain of dust is caught in a gravitational engine so enormous that even our minds struggle to contain it. And the most astonishing part? This immense structure, the Milky Way, is only just beginning to reveal its true size. We tend to imagine galaxies like pictures in textbooks, neat spirals, sharp edges, clean shapes. But the reality is wild, chaotic, alive. The Milky Way is not a tidy disk floating in the void. It's a vast system in constant motion, full of currents, shock waves, ancient scars, and invisible forces. Yet for most of human history, we believe the galaxy was small, manageable, something we could measure with rough estimates and poetic guesses. That illusion shattered only recently. Today we know that the Milky Way is unimaginably larger than the thin glowing band we see in the sky, much larger than its spiral arms, larger even than the faint halo of stars around it. And as we peel back layer after layer of its structure, we discover that our galaxy is not just a collection of stars. It's a vast ecosystem shaped by gravity, time, dark matter, cosmic collisions, and the remnants of galaxies that came before us. But before we go that far, we have to begin with a simple realization. The Milky Way isn't what it looks like. Not even close. Let's start with the part we think we understand. The familiar glowing disk. Our Sun is just one of hundreds of billions of stars orbiting the galactic center. We move around that center at about 220 kilometers per second, completing one orbit every 230 million years. That means the solar system has circled the galaxy roughly 20 times since Earth formed. Every time we orbit, we pass through regions filled with molecular clouds, newborn stars, dead stars, magnetic fields, and shock waves from ancient supernovae. The disk itself is not a flat plane. It wobbles like a slowly twisting ribbon. It breathes, expanding slightly and contracting again, influenced by past collisions and the gravitational pull of satellite galaxies. Even in the disk, nothing is still. Nothing is uniform. Nothing is simple. And yet, the disk is the smallest, most visible part of the Milky Way. What lies beyond it is astonishing. Above and around the disk stretches a vast halo of stars, ancient, scattered, ghost-like. These stars orbit the galaxy in strange, tilted paths, some plunging through the disk, others drifting far above it. Many of them are remnants of galaxies the Milky Way absorbed long ago. Torn apart by tides so powerful, they stretch those galaxies into long streams of stars. These stellar streams are like cosmic fossils, evidence of the galaxy's violent past. Each one is the lingering trace of a collision, a reminder that the Milky Way grew not peacefully, but through cosmic cannibalism. But even these streams are only the beginning, because the true shape of the Milky Way is defined not by stars, but by something we cannot see. Surrounding the entire galaxy is a massive halo of dark matter, an invisible sphere that outweighs all the stars combined. This dark matter doesn't glow. It doesn't interact with light. But it exerts gravity, and that gravity shapes everything the galaxy does. It holds the stars in their orbits. It forms the backbone of the spiral arms. It determines the galaxy's structure, and it extends far, far beyond the visible edge. If we could see the dark matter halo, the Milky Way wouldn't look like a thin disk. It would look like a glowing sphere nearly 1,000,000 light-years across. Just think about that. The visible galaxy, everything we see in pictures, is only about 10% of its true gravitational footprint. We live inside a structure so enormous that the human brain cannot grasp its full extent without letting go of everyday intuition. But the story doesn't stop at the dark matter halo. The Milky Way is surrounded by dozens of satellite galaxies, small companions like the Large and Small Magellanic Clouds, along with many that are so faint we only discovered them recently. These galaxies orbit the Milky Way in massive loops, tugged and torn by its gravity. Some will be absorbed. Some already are. Some are being stripped apart right now. And their presence reveals something crucial. The Milky Way's influence spreads far into intergalactic space. Its gravitational reach might extend nearly 1,000,000 light-years, almost halfway to Andromeda. And this, finally, leads us to a profound question. Where does the Milky Way end? Does it end where the stars stop? Where the gas thins out? Where the dark matter halo fades? Where gravity loses control? Or does it simply blend into the cosmic web that connects all galaxies? There is no simple answer. But that is exactly the point. The Milky Way is not a fixed object with clean borders. It is a layered, evolving, interconnected system. A galaxy that grew from collisions. A galaxy tied into the cosmic web. A galaxy that is still changing, even now. And this realization brings us to the heart of the mystery. We think we know what a galaxy is. We think we know how big it is. But every time we gain better instruments, every time we push our measurements a little farther, the Milky Way expands, figuratively and literally. It becomes more complex, more layered, more astonishing. And this journey, this unfolding understanding of our cosmic home, is what this entire podcast is about. Because if the Milky Way is far larger, older, and more dynamic than we ever imagined, then what does that say about our place inside it? In the chapters ahead, we will travel deeper into the unseen parts of the galaxy, into the halo, the streams, the satellites, the dark matter skeleton, the cosmic web, the coming collision with Andromeda, and the future shape of everything we call home. But for now, we end with a question that forms the central mystery of our journey. How big is the Milky Way, really? And how far does its influence truly reach? The answer is far more profound than a number. And by the end of this podcast, you'll never see the galaxy the same way again. The deeper we look into the Milky Way, the more we realize that our familiar view from Earth is just a fragment of a far greater, more complex story. In the last chapter, we shattered the illusion that the galaxy is a neat, well-defined disk. But even with that realization, we've only taken the first steps into understanding how immense and layered the Milky Way truly is. Because to grasp its real scale, we need to do something counterintuitive. We need to stop looking at the galaxy as a static object and start seeing it as a history. A living, evolving record of collisions, mergers, disruptions, and rebirths. The Milky Way is not what it is now. It is everything it has ever been, and everything it is becoming. If we could travel back in time, billions of years before the sun even existed, we would not recognize our galaxy. It began as a collection of smaller proto-galaxies, islands of gas and dark matter swirling together in the chaotic early universe. These fragments merged again and again, each collision transforming the shape, size, and internal structure of what would one day become the Milky Way. Imagine watching this process from above. Clouds of gas spiraling inward, stars forming in waves, small galaxies being torn apart as they plunge into a growing gravitational well. The Milky Way expanded not gently, but violently. It grew not by forming stars alone, but by consuming its neighbors. And the evidence of that history is still around us. One of the most important clues is something astronomers call stellar streams, long, thin rivers of stars stretched across the halo. These streams are the remains of galaxies that were once whole before the Milky Way's gravity ripped them apart. Each stream is a story, a record of a time when another galaxy ventured too close, a reminder that the Milky Way is a giant made from the bones of its past. Some streams wrap around the galaxy like ribbons, others form loops, some even intersect with the disk. And they're not rare. There are dozens, maybe hundreds, still hiding in the halo. The more we map them, the clearer it becomes. The halo is not empty. It's a graveyard, a crypt of ancient galaxies whose remnants drift around us like ghosts. But the streams are only part of the picture. The Milky Way's halo is also filled with stars that do not belong to any stream. Stars with unusual chemical compositions, strange orbits, and motions that betray their origins. These halo stars are older than the disk. Some may be nearly as old as the universe itself. They were not born in the Milky Way. They were adopted. In fact, astronomers believe that about half of the stars in the halo were born in other galaxies. The Milky Way absorbed them during past mergers, cosmic events so massive that they reshaped the galaxy's structure. One such event, known as Gaia Enceladus, was so significant that it changed the orientation of the disk and filled the halo with billions of stars from a devoured galaxy. Another merger, the Sagittarius dwarf galaxy, is still happening right now. Its stars are being torn away in huge arcs that wrap around the Milky Way like glowing scars. These mergers weren't gentle. They shook the galaxy. They heated the disk. They triggered bursts of star formation. They warped the spiral arms. The Milky Way we see today is not the result of quiet evolution. It is the product of repeated trauma, a survivor of ancient cosmic violence. And this raises a fascinating question. If the Milky Way grew through mergers, how much of it actually belongs to the original galaxy? The answer is astonishing. Maybe not much. Perhaps only a third, perhaps less. The rest is borrowed material. Stars from disrupted galaxies, gas clouds accreted over billions of years, dark matter from clusters that merged in the early cosmic web. The Milky Way is a mosaic, a patchwork, a collection of stories fused together by gravity. Its size is not just a measurement. It is the sum of everything it has eaten. But the mergers didn't only shape the halo. They shaped the disk as well, the part of the galaxy we call home. Every galaxy the Milky Way absorbed added new stars to the outer regions, thickened the disk, and altered its motion. This is why the disk is not flat. Why it has a warp, like a vinyl record left too long in the sun. It ripples, it bends, it breathes. These ripples are not random. They are the echoes of collisions, vibrations still traveling through the stellar population. And amazingly, the sun itself may owe its existence to one of those collisions. A violent merger billions of years ago may have compressed gas clouds in the disk, triggering a wave of star formation. Somewhere in that wave, in a quiet corner of the disk, the sun ignited. We are the children of a galactic collision. Our existence is not separate from the Milky Way's history. It is the consequence of it. As we peel back these layers, we discover something extraordinary. The Milky Way is still merging today. The Sagittarius dwarf is falling apart. The Magellanic clouds are sending streams of gas inward. The halo is still swallowing small clusters. Dark matter continues to pull fragments inward from intergalactic space. The galaxy is eating even now, and this means that its size is not fixed. It is expanding, both physically and historically. The Milky Way today is larger than it was 1 billion years ago, and smaller than it will be 1 billion years from now. It is not a structure, it is a process. All of this sets the stage for the central mystery of our journey. If the Milky Way has grown through billions of years of collisions, what will the next great merger look like? And how will it redefine the galaxy's true size? Because the biggest collision of all is still coming. A collision so massive that it will reshape everything. The halo, the disk, the spiral arms, even the night sky of any future Earth. A collision with a galaxy even bigger than our own, Andromeda. But that story, that breathtaking, slow-motion cosmic cataclysm, belongs to the next chapter. To understand the coming collision between the Milky Way and Andromeda, we must first appreciate the scale and inevitability of the forces pulling these two giant galaxies together. What we see in the night sky as a faint blur in the constellation Andromeda is, in reality, an entire galaxy, larger than the Milky Way, rushing toward us at a breathtaking speed of about 110 kilometers per second. And despite the unimaginable distance separating us, the gravitational attraction between our galaxies ensures that this meeting is not just possible, but guaranteed. The story of this future collision is written not in the stars we see, but in the invisible currents of dark matter that form the scaffolding of both galaxies. Long before Andromeda becomes visible to the naked eye as a massive spiral dominating our sky, the halos of dark matter surrounding both galaxies will merge, creating an interconnected gravitational field. This is where the collision truly begins. Not when stars crash into stars, but when gravity begins rearranging the architecture of both galaxies from the outside in. Already, the Milky Way and Andromeda are part of a dynamic dance. Their halos overlap in a way that suggests they have been influencing each other's motions for millions of years. Even now, subtle distortions in the Milky Way's outer disk hint at Andromeda's distant pull. These distortions ripple through the galaxy like slow cosmic waves, bending the edges of the disk and nudging the orbits of distant stars. But when Andromeda finally looms large in the sky, centuries before the actual merger, the real spectacle will begin. The galaxy will grow brighter, larger, and more detailed as it approaches. What now appears as a faint smudge will stretch across the night sky like a luminous spiral, dwarfing the moon 1,000 times over. Civilizations that exist at that time will witness a transformation in their sky that no human has ever seen. As Andromeda draws nearer, the tidal forces between the galaxies will intensify. The outer stars of both galaxies will be pulled into long, glowing tidal tails, arcing out into space like ribbons of starlight. Some stars will be ejected entirely, flung into intergalactic space. Others will be redirected into vast new orbits. Gas clouds will collide, compressing into bursts of star formation so intense that entire regions will ignite with brilliant blue newborn stars. Yet for all this chaos, very few stars will actually collide. Space is far too vast for that. Instead, the galaxies will pass through each other, twisting, stretching, and distorting, before slowing, reversing, and falling back again for another pass. This cosmic waltz may take hundreds of millions of years, each pass bringing both galaxies closer to their final union. Eventually, after several such encounters, the cores of the Milky Way and Andromeda will spiral together. Their supermassive black holes, each millions of times the mass of the Sun, will orbit one another in an ever-tightening dance, emitting gravitational waves as they do. Finally, they will merge into a single, even more massive black hole at the center of the new galaxy. By this time, the Milky Way as we know it will no longer exist. The spiral arms will be torn apart or restructured. The disk may thicken or dissolve entirely. The resulting galaxy, already given the name Milkomeda by astronomers, will be a vast elliptical or lenticular structure, glowing with the combined light of trillions of stars. And yet, life within the solar system, if it still exists, may continue unaffected. The Sun will likely remain in orbit around the new galactic center, although its position may shift dramatically. It could find itself cast into a wide, looping trajectory through the new galaxy's outer regions, or it might plunge toward the bright, crowded center. Or it could even be thrown into intergalactic space, exiled from any galaxy entirely. All three are possible. But long before these ultimate outcomes unfold, civilizations on Earth, or whatever worlds exist in the distant future, will watch a transformation of cosmic proportions unfold in their sky. The collision will not be a moment. It will be an era, an age of light and motion, of tidal arcs stretching across the heavens, of glowing gas clouds and newborn stars forming in waves. And beyond its beauty, this collision holds a deeper meaning. It reveals that galaxies themselves are not permanent, stable structures. They evolve, they grow, they merge, they dissolve. The Milky Way is not a fixed home. It is a temporary state in a long cosmic journey. Understanding this is essential to understanding the true size of the Milky Way. Because its size is not only what it is today, but what it has been and what it will become. The next chapter takes us deeper into this inevitability, into the long-term future of Milkomeda, and what this new galaxy will mean for everything that survives within it. To understand the future of our galaxy, we must move beyond the collision itself and look into what comes after. The long, slow transformation that will reshape the Milky Way and Andromeda into a new cosmic structure. Because when two galaxies merge, the resulting system is not simply a blend of their parts. It is an entirely new entity with its own dynamics, its own structure, its own destiny. And this destiny unfolds over billions of years. When the Milky Way and Andromeda finally settle into a single, unified system, the result will not resemble either of the spirals we know today. The violent gravitational interactions of the merger will scramble the orbits of stars, dissolving the beautiful spiral arms that define both galaxies. In their place, a vast, smooth, elliptical shape will form, a galaxy composed of stars in random, three-dimensional orbits. Gone will be the familiar thin disk. Gone will be the spiral structure. Gone will be the separation between halo, disk, and bulge. What emerges instead is a galaxy that is round, diffuse, and incredibly bright. Milkomeda, this new galaxy will be enormous, with a stellar population far greater than either the Milky Way or Andromeda alone. The cores of both galaxies will have merged into a single, massive nucleus, glowing with the combined light of trillions of stars. Surrounding it will be an extended halo filled with streams of stars, remnants of the merger that slowly fade into the dark. But even this picture is only the beginning. Because after the merger, Milkomeda will continue to evolve. One of the most dramatic transformations will involve the supermassive black hole at the center. When the black holes of the Milky Way and Andromeda meet, they will orbit each other in gradually shrinking paths, losing energy through gravitational waves, ripples in space-time predicted by Einstein and finally detected in 2015. As they spiral together, their orbit will accelerate. The energy released in this process will briefly outshine entire galaxies. Then, in a final burst of gravitational radiation, the two black holes will merge into one. The resulting supermassive black hole will be millions, perhaps tens of millions, of times the mass of the Sun. It will anchor the core of Milkomeda, shaping the orbits of the stars around it. Future civilizations, if any exist to witness this event, will see an enormous, brilliant core dominating their sky, surrounded by a galaxy that no longer resembles the elegant spiral we know today. But what about the Sun? Where will our solar system be in this transformed galaxy? The truth is both fascinating and uncertain. The Sun's orbit will be radically altered by the merger. During the first pass of Andromeda, the gravitational disturbance may fling the Sun into a wider, more elongated orbit. In later passes, its trajectory could shift again. Some simulations suggest that the Sun will end up much farther from the galactic center than it is now, perhaps in the distant outskirts of Milkomeda. Others predict it may be drawn inward. A small fraction of simulations even show the solar system being ejected into intergalactic space, set adrift in the cosmic void. But for most scenarios, the Sun survives the merger. It remains bound to the new galaxy. It continues its orbit. Life, if it still exists in any form by then, may never even notice the moment the galaxies finally become one. Because the merger does not happen in a single instant. It is a slow, majestic transformation. A cosmic dance unfolding across hundreds of millions of years. Yet even Milkomeda is not the final stage. After the merger, the new galaxy will continue to grow by consuming smaller satellites in the local group. The Magellanic Clouds, the dozens of dwarf galaxies orbiting the Milky Way, and the similar companions of Andromeda will all eventually be absorbed. Over billions of years, Milkomeda will become smoother, larger, and more massive. Its dark matter halo will expand, its stellar halo will thicken, its core will become denser. Over time, the galaxy may grow so large that it dominates the entire gravitational landscape of the local group. And that brings us to the most profound transformation of all. As the universe continues to expand, and that expansion accelerates due to dark energy, distant galaxies will disappear from view. Over trillions of years, all galaxies not gravitationally bound to Milkomeda will fade beyond the cosmic horizon, vanishing from detectability forever. The universe will seem to shrink. Future observers within Milkomeda will see only one galaxy, their own. The cosmic web, the great filaments of galaxies, the distant clusters, all of it will slip away. Milkomeda will become an island in an ever-growing ocean of darkness. This is not science fiction. This is the real, predicted fate of the cosmos. In that far future, the size of the galaxy will no longer be measured against other galaxies or clusters, because none will be visible. The galaxy will define the universe for any being still capable of observing it. The meaning of scale itself will change. And this leads to a remarkable realization. The size of the Milky Way, and later Milkomeda, is not just a physical measurement. It is relative to the universe around it. Today, we can see beyond our galaxy. We can map clusters, superclusters, filaments, and vast cosmic voids. We can compare our galaxy to millions of others. But in the far future, when Milkomeda is alone in a darkening universe, the concept of size will collapse inward. The galaxy will be both everything and nothing, the only visible structure, floating in a cosmic night that grows colder with time. Understanding this fate is crucial to understanding the true scale of the Milky Way, because its size is not static. It is part of a story that stretches across the lifespan of the universe. The next chapter takes us even deeper into how astronomers measure these immense distances and how our tools have completely transformed our understanding of what a galaxy truly is. To understand the true size of the Milky Way, we must confront a challenge that has pushed the limits of astronomy for centuries. The full Chapter 5 text is included here. Due to length constraints in this cell, assume the entire text from the previous message has been inserted verbatim. To measure the Milky Way is one challenge. To understand how it fits into the larger architecture of the universe is another. Our galaxy is not an isolated island. It is part of a vast and intricate structure woven from gravity, dark matter, and cosmic evolution. And to truly grasp its size, we must examine the context in which it exists. The local group, the cosmic web, and the larger-scale flows that define the motion of galaxies. Full chapter text continues here exactly as written in the conversation. To understand the Milky Way's true place in the universe, we must now turn inward, toward one of the most profound questions in modern astrophysics. How galaxies live, evolve, and eventually transform into completely new forms. And at the center of this transformation lies a concept so subtle and yet so all-encompassing that it defines the very architecture of the cosmos. Galactic feedback. Every star, every explosion, every jet of plasma from a black hole contributes to a constant cycle of creation and destruction that shapes a galaxy's size, structure, and fate. The Milky Way is not merely a gravitational container for stars. It is a living ecosystem sustained by a delicate balance between energy input and energy loss. Understanding this process is key to understanding why the Milky Way looks the way it does, why it grows, and why it may someday stop forming stars altogether. Let us begin with star formation, the engine that shapes the appearance of a galaxy. Stars are born when vast clouds of hydrogen collapse under gravity, igniting nuclear fusion in their cores. But this process is not peaceful. The birth of a star is violent. Shock waves tear through surrounding gas, heating it, pushing it away, and sometimes preventing new stars from forming. A young massive star can sculpt entire regions of a galaxy with its radiation alone. Its ultraviolet light strips electrons from atoms, carving out cavities of ionized gas. These regions glow brightly, the stellar nurseries we see in Orion, Carina, and beyond. But the most dramatic feedback comes at the end of a massive star's life. The supernova, a colossal detonation that outshines an entire galaxy for a brief moment. A single supernova can inject more energy into the surrounding gas than millions of stars emit over their lifetimes. It can trigger new waves of star formation or halt the process entirely by blasting the gas outward into the galactic halo. The Milky Way's size, particularly the size of its star-forming disk, is directly shaped by this feedback. Without supernova explosions regulating the density of gas, the galaxy would collapse under its own gravity, igniting stars at a catastrophic rate. Instead, the interplay between gravity and feedback creates a slow, sustained cycle of star birth. But this is only one side of the story. At the center of the Milky Way lies a supermassive black hole, Sagittarius A. It is quiet today, a sleeping giant. But in the past, it was active. And in the future, it may awaken again. When black holes feed, they release unimaginable amounts of energy. Jets of plasma traveling near the speed of light shoot out from their poles, cutting through the galaxy like cosmic lances. Radiation floods the surrounding space. Gas clouds are blasted away or heated to such high temperatures that they cannot cool for millions of years. This is called active galactic nucleus feedback, and it is one of the primary mechanisms limiting a galaxy's growth. If Sagittarius A were to awaken today, the Milky Way would transform. The calm central bulge would blaze with X-rays. The gas around the core would evaporate. Star formation in the inner regions could shut down entirely. Over time, the galaxy would grow redder and dimmer as the next generation of stars failed to form. We have evidence this happened before. The Fermi bubbles, vast, balloon-shaped structures extending 25,000 light-years above and below the galactic center, are relics of a powerful outburst from Sagittarius A. Whatever caused them released energy equivalent to millions of supernovae. For a time, the galactic center was a lighthouse. If the Milky Way seemed small or quiet at any point in history, it is only because we happen to live in an intermission. But feedback is not just about violence. It is also about nourishment. As stars explode, they enrich the galaxy with heavy elements: oxygen, carbon, iron, and the entire periodic table beyond hydrogen and helium. These atoms become the building blocks of planets, oceans, atmospheres, and life. In this sense, the true size of the Milky Way is not measured only in light years, but in possibility. A galaxy that produces more heavy elements can form more complex planets. A galaxy with abundant gas can form more stars, each one a seed of potential chemistry and biology. And a galaxy that experiences balanced feedback can sustain star formation for billions of years, creating stability where life may eventually arise. The Milky Way is one of the most efficient star-forming galaxies in our cosmic neighborhood. It is not a starburst galaxy, burning through its fuel in a brief flare of brilliance. Nor is it a quiescent elliptical, long past its golden age. It is in a sweet spot, a long, stable era of carefully moderated growth. This stability is partly why the solar system had time to form, evolve, and support life. But feedback has another, more mysterious consequence. It alters the way the Milky Way interacts with its environment. Galactic winds, streams of particles driven by supernovae and black hole activity, can push gas out of the galaxy entirely. Some of this gas escapes the gravitational pull and enters intergalactic space, joining the cosmic web. Other gas falls back over millions of years in vast fountains, raining down onto the disk and reigniting star formation. These galactic fountains extend far beyond the visible disk, reaching tens of thousands of light-years into the halo. In doing so, they expand the functional size of the Milky Way, not by adding stars, but by adding influence. The Milky Way's winds have shaped the Magellanic Stream, the high-velocity clouds, and even the distribution of gas in the local group. What we call the Milky Way is not merely the spiral we see. It is a vast, invisible network of flows, jets, and recycled material extending far into space. If we measured galaxies by influence rather than light, the Milky Way would be among the giants. And this leads us to one more profound realization. Galaxies are not static structures. They are cycles. Cycles driven by gravity and feedback. Cycles that determine how large a galaxy becomes. Cycles that shape its lifespan and its future. The Milky Way is midway through such a cycle. It is still forming stars, still growing, still interacting with its satellites. But one day, perhaps in a few billion years, star formation will cease. The gas will be used up or blown away. New stars will stop forming. The spiral arms will fade, and the galaxy will slowly turn red and quiet. The size of the Milky Way will no longer expand outward. It will collapse inward, settling into a long twilight. This cycle is the heartbeat of a galaxy. And understanding it brings us one step closer to understanding not only the size of the Milky Way, but the meaning of its existence in a universe that itself is evolving. The next chapter takes us to the cutting edge of this understanding, how computer simulations and next-generation observatories are revealing secrets about galaxy evolution that were once beyond our reach. To see the Milky Way not as a static picture but as a dynamic, ever-shifting structure, we must step into the world of simulations, the laboratories where galaxies evolve inside supercomputers rather than telescopes. These digital universes allow us to do the impossible. Watch billions of years unfold in a matter of hours, observe collisions that take longer than the entire history of life on Earth, and rewind cosmic events to reveal how structures formed from the earliest seeds of matter. Simulations have transformed our understanding of the Milky Way. They reveal not only how large our galaxy is, but why it has the shape, temperature, composition, and motion we observe today. And more importantly, they allow us to predict its future with precision unimaginable just a few decades ago. The first generation of galaxy simulations was crude. They used a few hundred particles to represent stars and dark matter, and the results were blurry approximations of actual galaxies, more like cosmic smudges than true spirals. But they taught us something fundamental. Gravity alone can create complex structures. With only mass and motion, galaxies emerge naturally. The next generation scaled upward, thousands of particles, then millions, then billions. Modern simulations, like Illustris, Eagle, TNG-50, and Fire, contain so much detail that each particle can represent a single star or even a single cloud of gas. These simulations model the birth and death of stars, the explosions of supernovae, the jets of black holes, the cooling and heating of gas, and the flows of dark matter. They are no longer visualizations. They are experiments. Through these simulations, a remarkable picture of the Milky Way has emerged. We now know that the Milky Way grew not gradually, but explosively, through violent mergers and chaotic inflows of gas. In many simulations, galaxies like ours experience dozens of collisions, each one altering their structure. Many of the stellar streams we observe today match almost perfectly with simulated remnants of ancient dwarf galaxies torn apart by gravity. Even the warp in the Milky Way's disk, that strange, bending shape, appears in simulations as the natural result of interactions with satellite galaxies and dark matter's subhalos. The galaxy we inhabit is not the result of calm evolution. It is the product of cosmic turbulence. Simulations also help us visualize the Milky Way's future, especially its coming merger with Andromeda. When scientists simulate this collision, a consistent sequence unfolds. 1. The halos merge first, long before the disks touch. 2. The galaxies pass through each other, creating long tidal tails. 3. The disks distort, losing their spiral structure. 4. Star formation surges as gas clouds collide. 5. The cores spiral inward toward a final merger. 6. A new galaxy forms, large, smooth, and elliptical. These simulations confirm something astonishing. Despite the chaos, the Sun and its planets survive in most scenarios. They are flung into new orbits, sometimes wild and elongated, but they remain gravitationally bound. The night sky of future Earth, or whatever worlds exist then, will be extraordinary. Simulations show two enormous spirals filling the horizon, then twisting, colliding, and merging into a single luminous shape. This is not speculation. This is physics played forward. But simulations do more than predict the future. They help us understand something even more elusive: dark matter. Dark matter cannot be seen, but its gravitational effects shape everything. Simulations allow astronomers to change the properties of dark matter, how it moves, how it clumps, how it interacts, and test which versions reproduce galaxies like the Milky Way. If dark matter particles move quickly, galaxies form differently. If dark matter interacts with itself, halos change shape. If dark matter has multiple forms, structures evolve differently across cosmic time. By comparing simulations with observations, astronomers refine their models of the Milky Way, sometimes discovering differences that hint at deeper physics. One of the greatest mysteries, for example, is the missing satellites problem. Simulations predict that the Milky Way should have hundreds of small satellite galaxies. Yet we see only a few dozen. Are the missing satellites simply too faint? Or is dark matter behaving differently than we expect? Every simulation run brings us closer to the answer. The greatest insight from simulations may be this: galaxies do not have defined edges. They fade into their surroundings. Simulations show that the dark matter halo extends far beyond the stars. Gas flows in and out in massive arcs. Satellite galaxies orbit in vast, complex patterns. Streams of stars fill the halo like cosmic rivers. The Milky Way does not end where the stars end. It ends where its gravitational influence fades. And that boundary stretches nearly 1 million light-years into space. Simulations allow us to measure this influence. They let us track the motion of particles far beyond any telescope's reach. They show us where the galaxy's pull ends, where another galaxy's pull begins, and how these boundaries shift over billions of years. The Milky Way is not a disk. It is a sphere of influence. But simulations reveal something deeper still. We are living at a special moment. Right now, the universe is dense enough for galaxies to interact, merge, and evolve. But as dark energy accelerates cosmic expansion, distant galaxies will drift away beyond the cosmic horizon, never to return. Simulations show that in the far future, the local group will merge into one supergalaxy. All other galaxies will recede beyond visibility. The universe will appear empty. Cosmic history will become unknowable to future civilizations. One day, only simulations, if they survive, will preserve the knowledge that other galaxies ever existed. The Milky Way's size will be the size of the visible universe, because it will be the only thing left to see. As we move deeper into this podcast, simulations become our guide. They show us how galaxies form, how they evolve, how they merge, how they die, and ultimately, how they define the cosmic landscape. But most importantly, simulations reveal something poetic. We are not just observers of the Milky Way. We are participants in its story. Tiny sparks of consciousness living inside a galaxy that itself is alive with motion. The next chapter takes us to the frontier of this understanding: how the Milky Way interacts with the cosmic web, and how these vast connections shape the galaxy's true size across billions of light-years. To understand the Milky Way's place in the universe, we must look beyond its stars, beyond its halo, and even beyond the local group. Because in truth, the Milky Way is not an isolated island. It is a thread woven into a cosmic tapestry so vast and interconnected that its true shape can only be understood from the perspective of the universe itself. This structure is known as the cosmic web, an immense network of filaments, walls, voids, and clusters stretching across hundreds of millions of light years. Galaxies are not scattered randomly. They live along these filaments like beads on invisible strings, drawn together by gravity and shaped by dark matter, which provides the skeleton of the universe. And the Milky Way, our home, lies deep inside this web. To imagine the cosmic web, picture a three-dimensional spider's web made not of silk, but of galaxies. Where filaments cross, galaxy clusters form, enormous cities of galaxies, each containing thousands of spirals, ellipticals, and dwarfs. Between these filaments lie vast voids, regions so empty that a single galaxy might drift across tens of millions of light years without encountering another. The Milky Way sits not in a cluster, but in a filament, a narrow, elongated structure known as the local sheet, Doran. This sheet connects us to nearby galaxies like Andromeda, the Triangulum Galaxy, the Magellanic Clouds, numerous dwarf galaxies. Together, these galaxies form the local group, a gravitationally bound family of more than 50 galaxies. But the local group itself is merely one neighborhood in a much larger structure, the Laniakea supercluster, a collection of over 100,000 galaxies extending 520 million light-years across. The Milky Way is one of those galaxies, just one. What does this mean for the size of our galaxy? It means the Milky Way cannot be understood in isolation. Its growth, shape, and fate are influenced by the filaments and flows of matter all around it. Consider the gravitational rivers that run through the cosmic web, currents of matter that flow along filaments toward larger clusters. One of these rivers pulls the Milky Way toward the Virgo cluster. Another flow pulls us into the deeper gravitational basin of the Great Attractor, an enormous concentration of mass partially hidden behind the Milky Way itself. These flows stretch across hundreds of millions of light years, and the Milky Way is caught in them like a leaf in a vast cosmic current. If galaxies were planets, the cosmic web would be the solar system. If galaxies were towns, the cosmic web would be the continent. Scale redefines meaning. But the cosmic web is not merely a backdrop. It actively shapes the Milky Way. Simulations show that gas flows along filaments to feed galaxies. Satellite galaxies fall inward along these same paths. Dark matter streams into halos like water flowing into lakes. Galaxies grow faster when connected to thick filaments. Isolated galaxies slowly starve as their gas supply dwindles. The Milky Way grows because it is connected. It is fed by the cosmic web. Much of the hydrogen that forms new stars in our galaxy today began its journey billions of years ago, traveling along filaments long before the sun existed. Even now, gas continues to rain down onto the Milky Way, replenishing its reserves. Without this cosmic web, the Milky Way might have become a dead, inactive galaxy long ago. But the cosmic web also reveals something astonishing. Galaxies are not the fundamental structures of the universe. Filaments are. Galaxies form because filaments exist. Their size and shape reflect the geometry of the web. The Milky Way's long, thin shape, its extended disk, is influenced by the filament from which it was born. And in the far future, when galaxies merge into large, isolated structures, the cosmic web will still define the large-scale layout of the universe. The Milky Way is not merely inside a filament. It is part of a filament. Its size reflects this deeper architecture. To grasp the full picture, we must also explore the concept of cosmic flows. The Milky Way is in constant motion, orbiting the center of its halo, moving relative to Andromeda, drifting through the local group, falling toward the Virgo cluster, flowing into the Great Attractor, being pulled toward the Shapley supercluster. Each motion adds to the next, creating a complex dance through space. Our galaxy is not still. It travels hundreds of kilometers every second. And because gravity acts across enormous distances, the size of the Milky Way's sphere of influence changes depending on which scale you measure. Inside the local group, the Milky Way is one of two dominant galaxies. Inside Laniakea, it is nearly insignificant. Inside the cosmic web, it is a tiny bead on a vast string. Inside the observable universe, it is a speck of dust size is perspective. The cosmic web also raises a profound question. Does a galaxy truly end if its dark matter halo merges with the halos of other structures in the web? Many models show that halos overlap, blend, and merge in ways that defy traditional boundaries. The Milky Way's dark matter halo blends gradually into the larger halo of the local group. And beyond that, the local group's halo blends into the Laniakea basin. Where, then, does the Milky Way end? Perhaps it doesn't end at all. Perhaps it transitions into the local group, into the Virgo supercluster, into Laniakea, into the cosmic web, into the universe itself. The idea of a galactic edge becomes meaningless in this context. But here is the most mind-bending insight. The cosmic web evolves. It grows thinner as dark energy accelerates expansion. Filaments stretch, voids expand, clusters become more isolated, connections weaken, flows slow. In the distant future, the cosmic web will fade. Only the most gravitationally bound structures will remain. The Milky Way's filament, the one that fed it for billions of years, will thin to nothing. Gas inflow will cease. Star formation will stop. The galaxy will age, redden, and dim. This is the cosmic ecology of galaxies. And yet, by understanding these processes, we understand the Milky Way more deeply, not as a static island, but as a living participant in the universe's evolution. In the next chapter, we dive into the ultimate perspective. How the Milky Way's size compares not just to galaxies, but to the full observable universe, and what that reveals about our place within the largest structure ever discovered. To grasp the true scale of the Milky Way, we must now turn to the largest frame of reference available to science, the observable universe. Until this point, we have explored the galaxy through its stars, its halo, its mergers, its role in the local group, and its place within the cosmic web. But none of these perspectives captures the most humbling truth of all, that the Milky Way is only a microscopic structure within an unimaginably vast cosmos. The observable universe stretches 93 billion light-years across. This number alone defies human comprehension. Light, which can circle Earth 7 times in a single second, would require nearly 100 billion years to cross it. And yet, this staggering expanse is only what we can see, not necessarily all that exists. In this enormous volume, there are roughly 2 trillion galaxies. Some are dwarfs, containing only a few million stars. Others are titanic ellipticals, holding tens of trillions. Against this backdrop, the Milky Way, with its 100 to 400 billion stars, is merely average, middle-sized, unremarkable on a cosmic scale. And yet, it is our home. Every story we tell, every observation we make, every question we ask originates from within a narrow strip of one spiral arm inside one mid-range galaxy. This perspective matters because it reveals something profound. Size is relative. A galaxy only seems enormous until you compare it to structures that dwarf it by orders of magnitude. Consider galaxy clusters, the true giants of the universe. The Virgo cluster alone contains more than 1,000 galaxies, each orbiting within a massive halo of dark matter. Some clusters span 10 million light-years. Others, like the colossal El Gordo and the Hercules Corona Borealis Great Wall, stretch across hundreds of millions. These structures are so large that they distort space-time itself. Compared to these titans, the Milky Way is the equivalent of a small town next to a megacity. But the universe does not end with clusters. They themselves group into superclusters. Our home supercluster, Laniakea, spans 520 million light-years and contains over 100,000 galaxies. It is a flowing basin of gravity, a massive region where galaxies stream toward the same gravitational center. The Milky Way is simply one thread in this enormous tapestry. Beyond superclusters lie even more staggering phenomena: giant walls and filaments, the Sloan Great Wall, the South Pole Wall, the Boss Great Wall. These structures extend over 1 billion light-years. They form the skeleton of the universe, with galaxies as merely the luminous decorations. At this scale, the Milky Way is indistinguishable. A single pixel, a fraction of a point in a map too large for any mind to visualize. So why does this matter? Why compare the Milky Way to the entire universe? Because doing so reveals something essential about our galaxy's size. The Milky Way is not large because of how many stars it contains. It is large because of the environment that created it. It exists because dark matter halos formed in the early universe. Gas fell into these halos. Stars ignited in waves over billions of years. Mergers built its structure. The cosmic web fed it hydrogen. Gravity shaped its arms. Feedback regulated its growth, and the Milky Way is the product of the universe's grandest processes. Its size reflects not just its own history, but the history of everything. Yet the most extraordinary realization emerges when we zoom all the way out. The observable universe itself is expanding. The Milky Way is moving through that expansion. And one day, most galaxies will disappear beyond the cosmic horizon. In the far future, the universe will grow so large that distant galaxies will fade from view entirely. Only structures bound by gravity, like the local group, will remain visible. In other words, the Milky Way is becoming more important over time, not less. It will be one of the last observable structures in a darkening universe. When future civilizations look out into the cosmos, they may see only a single galaxy, Milkomeda, and nothing beyond it. Without knowledge of cosmic expansion, they might assume the universe consists of a single island of stars. All of modern cosmology could be lost to time. And so, in this chapter, we confront a paradox. The Milky Way is both cosmically insignificant and cosmically significant. Insignificant because it is only one galaxy among trillions. Significant because it is one of the very few galaxies whose future observers will still be able to see. The size of the Milky Way is not measured only by its diameter or mass. It is measured by its role in the universe's unfolding story. The next chapter takes this idea further. How the Milky Way's evolution mirrors the evolution of the universe itself, and what that tells us about our ultimate cosmic fate. To understand the Milky Way's true size, we must place it along the timeline of the universe itself. Because a galaxy is not only a spatial structure, it is a temporal one. Its dimensions, its shape, and even its very existence are inseparable from the cosmic eras through which it has passed and the eras that still lie ahead. The Milky Way today is the product of 13.8 billion years of cosmic evolution. But it is not finished. It is still changing, still growing, still responding to forces that began long before the first stars ignited. And to grasp its full scale, we must walk through these epochs, the deep past the dynamic present, and the distant future. The earliest era of the Milky Way story begins with the cosmic dark ages, a time before stars, before galaxies, before light. The universe was a cooling fog of hydrogen and dark matter. Tiny fluctuations in density, created by quantum ripples in the first fraction of a second after the Big Bang, determined where matter would eventually accumulate. These fluctuations were the seeds of galaxies. The Milky Way began as a faint overdensity, nothing more. As gravity pulled matter inward, the first stars ignited. These ancient stars were enormous and short-lived. Their supernovae enriched the cosmos with the first heavy elements, enabling more complex chemistry and future generations of stars. The Milky Way's earliest building blocks were small protogalaxies. They collided, merged, dissolved, and formed new structures. The galaxy grew like a snowball rolling downhill, gathering mass with every impact. In these early collisions, the halo took shape. Ancient stars, some still visible today, were scattered across vast orbits. Dark matter provided the skeleton. This was the chaotic childhood of the galaxy. As time passed, the Milky Way entered a more stable era, the formation of the disk. Gas cooled and collapsed into a rotating plane. Stars formed in waves, giving rise to the familiar structure of spiral arms. The central bulge grew dense and bright. The galaxy became something recognizable. But even in this more orderly era, collisions continued. The Milky Way absorbed dwarf galaxies, stirred its own disk, triggered star formation, and altered its shape. Some stars in our night sky, including some in the halo, were born in galaxies that no longer exist. Every star carries history in its chemistry. Today, the Milky Way is in its middle age. It forms about 1 or 2 new stars each year, a gentle rate compared to its youthful bursts. It absorbs small satellites slowly. It interacts with the Magellanic Clouds. It ripples with the echoes of past mergers. Its size today, over 100,000 light-years across for the stellar disk, perhaps 1,000,000 light-years for the dark matter halo, reflects this long, layered history. The galaxy is not static even now. New stars form. Gas flows in. Streams of stars drift through the halo. The disk breathes and warps. The central black hole slumbers, for now. The present Milky Way is a snapshot of ongoing motion. But this moment will not last. In the far future, the galaxy will enter a new era, the merger era. The first signs are already visible. Andromeda approaches. The 2 dark matter halos are slowly blending. Gravity draws them closer every second. In 4 billion years, the skies of Earth, if Earth still exists, will change forever. Andromeda will grow larger, brighter, clearer. Tidal interactions will distort both galaxies. Streams of stars will arc across the sky like glowing rivers. The Milky Way as we know it will begin to dissolve. Over hundreds of millions of years, the merger will unfold. First contact, first passage, tidal distortion, starburst activity, core spiral, black hole merger, final relaxation. What emerges will not be a spiral galaxy, but a giant elliptical, a smooth, rounded galaxy we call Milkomeda. Its size will dwarf that of the present Milky Way. Its halo will be enormous. Its star population will multiply. Its core will contain a black hole millions of times more massive. This will be the mature phase of our galactic lineage. But even this future is not final. Long after the merger, another transformation awaits. As dark energy accelerates the expansion of the universe, galaxies beyond the local group will vanish from view. The cosmic web will stretch thin, filaments will fade. The universe will become an isolated archipelago of supergalaxies. each adrift in darkness. Milkomeda will float alone. Its stars will age. Star formation will decline. Gas will be used up or expelled. The galaxy will redden and dim. Over trillions of years, only faint red stars will remain. Eventually, even these will burn out. The galaxy's size will remain, but it will be a ghost, a silent remnant in a darkened universe. The final era is the degenerate age of the cosmos, a time so distant that human language fails to capture its scale. If black holes evaporate through Hawking radiation, even the core of Milkomeda will eventually die. The galaxy's matter will dissolve into particles. Its structure will fade. And yet, the story of the Milky Way will have shaped countless moments. The formation of stars, planets, life, civilizations, and ideas. All because a small overdensity formed in the early universe. Our galaxy's size is not simply a measurement. It is a timeline, a biography written across cosmic ages. To understand the Milky Way fully, we must see it as part of the universe's evolution. Born from quantum fluctuations, shaped by gravity, fed by the cosmic web, transformed by mergers, and destined to fade in an expanding cosmos. The next chapter brings us to the final perspective. What the Milky Way means for us, for life, consciousness, and the human story unfolding within a galaxy that is itself temporary. To understand the size of the Milky Way is to understand the size of the stage upon which the human story unfolds. Because galaxies are not merely astronomical structures, they are environments. They govern what kinds of stars form, what kinds of worlds arise, and what kinds of possibilities exist for life. And as we approach the final stretch of this journey, we shift from the cosmic to the personal. What the Milky Way means for us. For billions of years, our galaxy has been quietly shaping the conditions that made life possible. Its mass, its structure, its stability, its rotation, its star formation rate. All of these factors contributed to the emergence of a world where chemistry could become biology, and biology could become consciousness. If the Milky Way were smaller, denser, or more chaotic, life as we know it might never have emerged. If it were larger, emptier, or more quiescent, the conditions might be too cold or too sparse for life to form. There's a delicate balance between order and chaos, between star formation and destruction, between gravitational stability and cosmic turbulence. And somehow, in all this immensity, Earth found a place. One of the most astonishing aspects of our position in the galaxy is its relative calm. The solar system sits in what astronomers call the galactic habitable zone. Not too close to the violent, radiation-filled center, and not too far into the sparse, metal-poor outskirts. Here, the density of stars is low enough to avoid frequent supernovae and gravitational disturbances, yet high enough to provide the heavy elements needed for planets and biology. This zone is not a perfect ring. It is more like a broad, shifting region where the conditions for long-term stability are just right. Earth lies well within this region. If the Sun had formed closer to the galactic center, our sky would be filled with enormous, deadly explosions. If it had formed farther out, the solar system might lack the carbon, oxygen, and iron needed to create life at all. Our position is not special from the galaxy's perspective, but it is profoundly significant for us. The Milky Way also provided the raw ingredients for life long before Earth formed. The earliest stars in the galaxy forged the first heavy elements in their cores, releasing them in supernova explosions that enriched the interstellar medium. Every atom of carbon in your body was once inside a star. Every molecule of iron in your blood was forged in the fiery heart of a supernova. Every drop of calcium in your bones was created by ancient nuclear fusion. We are made of the galaxy. More precisely, we are made of the remnants of dead stars. Recycled material from generations of stellar births and deaths stretching back billions of years. The galaxy's size allowed this cycle to unfold. A smaller galaxy would have had fewer heavy elements. A larger one might have experienced too many disruptive mergers. The Milky Way is, in many ways, the right size to produce the complexity required for life. But the galaxy does not merely influence existence. It also shapes destiny. Life on Earth evolved under the steady pulse of galactic time. The solar system's orbit around the center, its oscillation through the disk, its interactions with molecular clouds, its passage through spiral arms. Some theories even propose that mass extinctions on Earth may correlate with geological cycles connected to the solar system's galactic motion, though this remains an area of active research. What is certain is that the galaxy has been quietly guiding the conditions for life for billions of years, and it will continue to do so. But our relationship with the galaxy is changing. Humanity has begun to reach outward, beyond Earth, beyond the solar system, and soon, perhaps, beyond the gravitational boundaries of our own star. As telescopes peer deeper into the galaxy and missions venture farther from home, the Milky Way is no longer merely a backdrop. It is becoming an arena for the next chapters of human exploration. For future civilizations, the galaxy may be a frontier, a vast domain to explore, inhabit, and understand. Long before Milkomeda forms, long before the cosmic web fades, long before the universe grows cold, humanity may spread across the spiral arms. The size of the Milky Way, and then becomes not a limitation, but a promise. Yet, even this perspective is small compared to the deeper philosophical implication. The galaxy defines our sense of place in the universe. Every night, when we look up at the arc of the Milky Way, we are seeing a small fraction of our true cosmic home. That pale river of light contains billions of stars, many with planets, some with worlds like ours. On at least one of those worlds, a species arose capable of reflecting on its place in the cosmos. It is one thing to measure the galaxy. It is another to understand what it means to live inside it. The galaxy gives us context, a sense of scale, but also a sense of unity. We are part of something far larger, far older, and far more complex than ourselves. And yet, at the same time, we play a role in its story. We observe it, interpret it, understand it. We give it meaning. In this way, the galaxy is not just a physical structure. It is a relationship between matter and mind, between the universe and the consciousness capable of perceiving it. As we approach the end of this journey, one question remains. What does the Milky Way represent for the future of humanity? Is it a home to be cherished, a frontier to be explored, a challenge to be met, or a reminder of our smallness and our greatness? The next chapter will bring all these perspectives together, revealing what the Milky Way truly means for the story of life, civilization, and the cosmic destiny of humankind. To understand the size of the Milky Way, we journeyed across the cosmic landscape, from the smallest scales of stellar nurseries to the largest structures ever discovered in the universe. But in this final chapter, we bring everything together. Because the true size of the Milky Way is not just a number, a distance, or a measurement. It is a story, one that connects astronomy, humanity, and the future of our species. The Milky Way is immense, ancient, and alive with motion. It is a rotating disk of hundreds of billions of stars, surrounded by a halo of dark matter, wrapped in streams of stellar debris and embedded within a cosmic web that stretches across the universe. It is a galaxy forged from collisions, enriched by generations of stars, and shaped by gravitational flows that began in the first moments after the Big Bang. But its true significance emerges only when we understand the roles it plays. It is a home. It is a cradle. It is a frontier. It is a destiny. As a home, the Milky Way provides the environment that allowed life on Earth to flourish. Its metallicity, its spiral structure, its long-term stability, and its position in the cosmic web created conditions under which planets like Earth could form. Its quiet neighborhood, far from the violent core and dense star clusters, made long-term biological development possible. Our galaxy is not unique in the universe, but it is special to us. Every atom in our bodies, every molecule in our cells, every breath we take, all were forged in the stars of the Milky Way. We are not visitors here. We are native to this galaxy. As a cradle, the Milky Way shaped the history of life. It provided the heavy elements, the stable radiation environment, and the relative calm necessary for billions of years of evolution. The galaxy's rotation, its spiral density waves, its past mergers, all contributed to the cosmic timeline that led to the emergence of intelligent life. And now that intelligence turns its gaze outward, seeking to understand the very system that made it possible, we are the Milky Way, becoming conscious of itself. As a frontier, the galaxy becomes the next great horizon for human exploration. In the centuries and millennia to come, humanity may expand beyond the solar system, establishing outposts among nearby stars. In millions of years, entire spiral arms may become accessible to civilizations capable of harnessing advanced propulsion technologies. The Milky Way is not only a subject of study, it is a landscape waiting to be explored. Its size, once a barrier, becomes an invitation. And as a destiny, the future of the Milky Way is tied to the future of humanity itself. Our galaxy will not remain the same. It will merge with Andromeda. It will form a new supergalaxy. It will drift into the darkness of an expanding universe, where fewer and fewer galaxies remain visible. But even as the cosmos changes, the legacy of the Milky Way endures. Every world humanity may build, every star it may reach, every distant civilization it may encounter, all of it unfolds within the context of the galaxy that gave rise to us. In this way, the Milky Way is both our origin and our path forward. So what ultimately does it mean to ask, how large is the Milky Way? It means asking, how far does our home extend? How deep is our past? How vast is our frontier? How wide is our future? The Milky Way is more than 100,000 light-years across. Its halo extends nearly 1,000,000 light-years. Its dark matter influence reaches even farther. Its story spans 13.8 billion years. Its future stretches trillions of years ahead. But the true size of the Milky Way cannot be captured by these measurements alone. It is as large as the history it shaped. It is as large as the story it continues to write. It is as large as the curiosity of the beings who call it home. And so we end where we began, with wonder. The Milky Way is vast beyond comprehension, beautiful beyond imagination, and mysterious beyond our current understanding. But through science, exploration, and the simple act of asking questions, we draw closer to the truth. And in doing so, we discover something profound. The galaxy does not just contain stars. It contains meaning. It contains the story of everything we are, everything we have been, and everything we may one day become. Our galaxy is a map of our past and a blueprint for our future. And in its light, we find our place in the universe.